So the quiz, I hope everybody by now did the quiz, you know, and yeah, so I know I can see here the submissions, you know, I can see in Brightspace the submissions. Some people, you know, got a little problem submitting, and they sent me, you know, their copies. Okay, I think, you know, if you have the scanning apps, you know, there you have several of them. I think that you can go ahead and practice, you know, how to how to scan something, make it a PDF, you know, outside the quiz, you know, but just by yourself, you know, practice that, you know, until we go back fully to the face-to-face class, until we go back fully to that, we will have to deal with this stuff, this kind of, you know, stuff. All right. Okay, so today we finished how to multiply, you know, radicals. We finished that. So we practiced that, how to divide radicals also. So we're gonna go ahead and start that section about how to rationalize a denominator, right? So let me go ahead and um, share my screen. And, okay. So we're gonna go ahead and see. I think that is 3.5, if I'm not mistaken. Rationalizing the denominator, 3.5. Okay, so the word rationalizing means making it a rational number. This is what the word rationalizing means. Make it a rational number. So now, if you know what is a rational number, you see numbers. We have numbers of several types, right? You know, this is how we view numbers. Unfortunately, we don't insist too much on what type of numbers we have. We don't insist too much on that in these classes. We just, you know, talk about numbers. We never insist on what they are actually. So the very first numbers, as we can imagine, the very first numbers, rationalizing, I didn't write the O. The very first numbers are the counting numbers, right? You know, what numbers like, you know, 0, 1, 2, 3, 4, 5, 6, 7, 8, etc. These are what you call the natural numbers, you see. And then what people got at first are numbers like, you know, etc. And then they realize, according to the needs, these numbers are not enough, right, to describe reality. They are not enough. What they did, they invented negative numbers, you know, -4, -3, -2, etc., -1, and so on. All these numbers together, positive whole numbers, negative whole numbers. Somebody knows how we call them? Do somebody know how we call them? The positive whole numbers and the negative whole numbers. Do you know what name they have in math?
Are they prime?
No, they are not prime.
Is it integers?
Integers. Thank you very much. They are called integers. You see, so integers, an integer is a whole number, whether it is positive or negative. And then we realize they are not even enough, you know. You can imagine these numbers, if they were the only number that we knew, how are you going to divide $5 among like two people, you see? If these numbers were the only number that we knew, how are we going to divide $5 among like to two people, for instance? So that's why we need some more numbers. So we have decimal numbers. In particular, we have any number that can be put as a fraction. Any number that can be an integer divided by another integer. You see? Any number that can be written as an integer divided by another integer is called what? Somebody knows the name?
A fraction.
It is a fraction, but they have a, a math name. They have a name. Just like the integers, they also have a name for these. Any number that can be put as a fraction is called a rational number.
Okay.
Okay. A rational number is any number that you can write as a fraction. For instance, of course, this number 3/5 is a rational number, right? Okay, so if we say 0.8, why 0.8 can be viewed as a rational number? Why it is a rational number? Because it's very easy to write it as a fraction, right? What is the easiest way to write 0.8 as a fraction? You have a bunch of ways, but what is the easiest one? 0.8. Actually, we can write it what?
10.
8/10, right? You see, etc., etc. An integer like 6 is a rational number because 6 is 6/1, right? So when the decimal number never stops, right? Like 0.33333, etc., never stops, right? But it is repeating, you see? It keeps repeating. Okay, that is also this type of numbers, we can write them as fractions, right? There is a way to write them as a fraction. For instance, 0.3333, we all know is 1/3, right? Okay, so if the decimal number stops, it is of course a rational number. If the decimal number, if the decimal part never stops, but at one point of time is repeating, we have a repeating sequence, it is also a rational number. Now, some numbers, they exist in math. Some numbers will never be put as fractions, never. What type of number, for instance, do you know that is irrational? We call them irrational. Irrational number is a number that will never be able to write as a fraction. Do you have an example in your head?
Would 0 be one?
0 can be written as a fraction, like a lot of ways. 0 is 0 over any number. 0 is 0/5, is 0/7, right, etc. But you have some famous numbers. They are famous. One of them is very, very famous. That number is irrational. We can never write it as a fraction. It's a very famous number.
Is it pi?
Yes, it's pi.
Is it?
It's pi.
Give that lady extra credit.
Okay.
Yeah, this deserves extra credit. It is pi. See, pi is an irrational number. You will never be able to write pi as something divided by something, never. So, which means when we were kids, and when we were taught what was the value of pi. For instance, have you ever heard like pi is 3.14? They say actually, when we kids, we get taught pi is 3.14. It is not. That is wrong. That is a wrong. It's a wrong teaching. But we cannot teach to a kid. You cannot tell them pi is almost. You see, you cannot say when you say almost 3.14, you're gonna get confused them, right? Pi is not 3.14. Pi is like if you look at my calculator. So if I share my whole screen and then if I get the calculator out to get a value, an idea of how much is pi here. So do we have pi even? So this is scientific right here. So this, I don't guess this one. Okay, or let me just Google pi, The number of pi, you see, this is pi. You see how many decimals it has? The decimals never stop, you see. Yeah, somebody plays with the number pi is 3 point, you see, everybody sees this small stuff, 3.14, you see, 3.14, 159, etc., etc. The decimal part will never stop. Everybody see that? This is what is pi. So when you say 3.14, we are rounding. We stop at the first two. We round, right? We say pi is almost 3.14, but pi is what pi is. Pi is just a pi, right? So I mean, this pi is irrational. Okay, the pi is irrational. Now pi is irrational number. Some other numbers are also irrational. Among them, any square root, for instance, any radical that is not an exact number. You see, squares of 2, squares of 3, squares of 7, squares of 11, etc., etc. All these numbers are irrational. Cube root of 8. Cube root of 8 is an exact number, right? Cube root of 9, cube root of 25, etc. All these numbers are irrational. Okay? They are irrational. We cannot write them as fractions. All the numbers like you see here. And that is why here, when we say rationalizing the denominator, it means when my denominator has a square root, for instance, and I want a way to remove the square root, right? Okay, that is what you're going to see today. When my denominator, I have a fraction. In my denominator, I have a square root, for instance. I want to do something so the square root goes away. So before we do that, do you remember how we got, so what is squares of 5 times squares of 5? Do you remember that? Somebody?
25. It comes out, the 5.
It's come out 5, right? After, so squares of 11 times the squares of 11, we get what it end up to be?
11.
11. We don't need to do the math in between. We don't need to do 11 times 11, which is 121, and then we take the square root, which is 11. If they do match exactly, it gives you the number itself, right? We agree with that? Okay, so rationalizing the denominator, I was saying, is when we have, for instance, 1 over square root of 3 or 2, rationalizing the denominator means remove the denominator from the denominator. Remove the square root from the denominator. This is what we call rationalizing the denominator. When you remove the square root from the denominator, your new denominator becomes a rational number, right? Okay, so now look, because just me reminding you this, when you multiply square by itself, does it give you an idea what to do here? I know I want the squares of 2, the squares over the number 2 to be gone, to go. Okay? Me giving you these 2 examples right here. Does it give you any hint what to do here?
Multiply both sides by √2 over √2.
Thank you very much. You see, if I multiply the denominator by √2, I will have 2 squares of 2's, 2 of them, they cancel out, it will only 2, right? So here, and that is exactly the right answer, thank you. So you have 1 over √2. What I'm going to do here is I'm going to multiply and divide by the same square root. Multiply and divide by the same square root, right? Okay? So the only reason I do that is for the 2 squares at the bottom to cancel out, right? And we have 2. Okay? Everybody see that? This is how simple this example is. You multiply and you divide by the square root, which you see at the bottom, right? Okay, so this will be squares of 2 over 2, right? You see now my new denominator is free of square roots, right? So my new denominator is a rational number. This is what I wanted. But can you ask, you see what happens here? Originally, did we have any square root at the top? In the original expression, number, was there any squares at the top?
No.
No.
Look at the final answer. What do you see at the top now?
A square root.
Square root.
So we can say, well, okay, what's the point, you know? Okay, maybe you get rid of the square root at the bottom, but now you have a new one at the top, right? You know, if this was like, you know, a problem is like a transfer of a problem, right? Okay, if this was a problem, it's like you remove the problem from the denominator, now you put it on the numerator. But in OA3, we do some techniques that we don't know why, that we don't know the reason until we do calculus. If you do to calculus, for instance, you will have problems. In order to solve them, you have to do the transfer of square roots. You see, if the square was at the bottom, you do something to bring it at the top. If it was at the top, you do something to bring it at the bottom. Okay, but now we just see the technique now. We even don't know why we do it, actually. We don't know why we do it because we don't apply it. Okay, but if you keep doing math and you go to calculus, for instance, you will see why we did it in OAD3, why we did that, why we rationalize the denominator. You will see that, okay? You will see that reason. So the first examples are this simple. If you say 3 over square root of, you know, 14, right? To rationalize the denominator, what do you suggest? You have to multiply, divide by what? Multiply, divide by square root of
14.
Exactly, right? So now my new numerator will be 3 squares of 14 over 14. That's it. Okay. So again, you know, when I see something like that in the test, I don't overdo it. Do not overdo it, right? So we say 9 squares of 2 divided by, 5 square root of 7, right? I have to, my decision, is it motivated by the squares of 2 or by the squares of 7?
Square root of 7.
The squares of 7. I almost don't care about squares of 2, right? What I have to do is solely motivated by squares of 7. That's it. Because I want to remove the square root over the 7. If I have a square over the 2, I almost don't care about it. Okay, because my question is rationalize the denominator. You didn't tell me rationalize the numerator. If you told me rationalize the numerator, then I would care about the numerator. But when you tell me rationalize the denominator, I only care about the denominator. That's it, right? So then I have to multiply, divide by what?
Square root of 7.
Squares of 7, exactly. What's going to be my new denominator? 5 times what?
5 times 7.
5 times 7. And now the other one, the top one, I can say is 9 squares of 14. Everybody sees where the 14 come from? Everybody see where the 14 come from? 14 come from?
Yeah,
2 times 7.
Yes, 2 times 7. Will be 9 root of 14 over 35. Because this is how we rationalize numbers. So let me give you some problems you're going to do by yourself. All right. In each case, rationalize the denominator, please.
Can you go back?
Yeah, I was sharing the word. So now, can you see it now?
Yeah, thank you.
Mm. All right. Okay, so the first one, I guess, is the simplest one. So you have to do what? For the first one,
Multiply both sides by the square of 15.
exactly. Square of
Multiply by
15, square of 15. What's going to be your final answer?
the square of 15 over 15.
Yep, that's it. Squares of 15 over 15. We just stop right here. The second one, we're going to multiply the numerator and the denominator by what?
Square root of Wait, which one are we on? The 31 and the 13?
Yeah,
Square by the square root of 13.
exactly. Square of 13, square of 13. Thank you. So the first one becomes 3, a single square root, right? If I want to, and I have to do 13 times 31. How much is that?
403.
103. And then the denominator will be 5 times what?
13.
Exactly, 5 times 13, which is 3 squares of 403 over 65. All right.
You don't try to break down that 403?
I don't think it's gonna break down nice. Does it?
It's not gonna play nice. I don't know.
So I mean, if somebody can come up with nice numbers to break down for, when I say what I call nice numbers is at least one of them to be a perfect square.
I know. I like it.
If we cannot find it, I don't. 403 doesn't look like a nice number, you know. So we just stop right here. For the last one now, we have to multiply, divide by what?
Square root of 8.
Square root of 8, right? Thank you. So what you get at the top?
-6 square root of 16.
At the bottom we get?
4 times 8.
Thank you. And then in this case, you see in this case, square root of 16 is how much?
4.
4. It's going to be -6 times 4 over 4 times 8. You know, we can simplify. You can -3 over 4, right? So if you can simplify, we go ahead, we simplify, you know. But here, what we're learning here is not how to simplify. What we're learning here is what to do to rationalize the denominator in this case. Again, this is like a very simple case. So on the test, or when you see that on the test, please do not overdo it, right? Don't do it like too much, okay? It's like very simple. You multiply and you divide by the square root you see at the bottom. You have the second case, which is not very, very simple. Look, right here. Can you do this? Before we do the second case, can somebody do square root of 7 minus 2 times the square root of 7 plus 2? We have a long way and we have a short way. Okay? We have the long way and we have the short way. The long way would be to distribute, right? That is a long way. Can you distribute that and simplify it a little bit?
Well, you already know 2 square roots of something is just the regular number. So it'll just be 7.
So that is the first arrow is 7. I agree with you. What is the next one?
2 square root of 7.
2 squares of 7. What is the next one?
-2.
-2 what?
Square root of 7.
What happens to them two?
They cancel out.
They cancel out. And what is the last one?
-4.
-4, which is 3, right?
3.
Okay. You see, when I multiply them, what I happened originally, what I had originally in the parentheses, I see parentheses, I see square roots, right? But look at the final answer. Do I have any square roots in the final answer? We don't have any square in the final answer. Okay, keep that in mind. Originally, I had square root, but when I multiply them together, I don't have squares anymore. But now this is like the long way is to distribute. The short way, look at the expression, right? They remind you of what formula?
Difference of 2 squares.
Thank you very much. Difference of two squares. That's very good. Because when I look at them, I see the first one looks like, to me, the first one looks like a minus b, right?
Yes.
The second one looks like a plus b. And all of you recall, what is a minus b put next to a plus b? This is the difference of two squares. This is a squared minus b squared, right? Okay, this is a squared minus, everybody remember that? By the way, you have to remember this formula until the end of the semester, right? This is a squared minus b squared. So who plays my a here?
Square root of 7.
Square root of 7 square. Who plays my b?
-2.
Is 2, right? Minus 2 square. How much is square of 7 all square? Don't they cancel out? It's 7 minus 4, which is 3. Okay?
Hot dog.
You see, that way, every time you have difference of two squares, take advantage of it. It's going to save you some distribution time, right? But you have to make sure it looks like a plus b, a minus b, right? You have to make sure it does look like a plus b, a minus b. When it does look like a plus b, a minus b, you don't need to distribute. I mean, you could distribute, but it's a waste of time. It's a squared minus b squared, right? Okay, so how we call them, a plus b and a minus b are called conjugate. So square of 7 minus 2 and square of 7 plus 2 are conjugate, right? That is a new word for you, right? So basically we're saying the conjugate of a plus b is a minus b. The conjugate of a minus b is a plus b, you see? The conjugate of a minus b is a plus b. The conjugate of a plus b is a minus b. So when we multiply two conjugate, we get a difference of squares, right? Okay, so look right here. What is, if I have a square root of 13 plus square root of 5, what is the conjugate of this one? Tell me, what is the conjugate of this expression?
Square root of 13 minus square root of 5.
Thank you very much. You just change the middle signs, that's it. So 13 minus square root of 5. When I multiply them, again, to repeat again, do we need to FOIL?
No.
We don't need to FOIL. This is a plus b, a minus b. What is a plus b, a minus b? It's the difference of squares, right? It's going to be squares of 13 all square minus squares of 5 all square, right? Which is 13 minus 5, which is, because the squares cancel out, right? It's going to be 8, you see? In each case, look what happened. Look at the final answer. Do you see any square roots in the final answer?
No.
We don't see no squares in the final answer. So we're going to keep that in mind. So now, that's going to be our second case now. If I have this now, I have 1 over square root of 11 minus 3. I want to rationalize this denominator. I want to do something to remove the square root from the denominator. Now look now. Multiplying only by the same square root, does it do the job? If you multiply by square root of 11 on both sides, does it do the job? If you do multiply by square root of 11 plus square root of 11, is that it?
Maybe do +3?
Yes, that's going to be exactly. My point is now, our technique in the first part doesn't work anymore, right? The technique from the first part doesn't work because now here when you multiply this by this, okay, you may free this square root, but then you're going to introduce another square here, right? So this doesn't work anymore. What you're going to do exactly is what we did. We're going to take inspiration. We're going to take inspiration from these examples right here, right? What I put next to the, what I'm going to put next to the square root of 11 minus 3? What I'm going to put next to it?
+3.
I'm going to put square root of 11 plus 3, the conjugate, right? Everybody see the reason? My inspiration comes from these examples right here, because when I put two conjugates next to each other, my product is free of square roots, right? Okay, but since I divided by square root of 11 plus 3, what I have to put here at the top? Same thing, right?
Square
Basically, what is the technique? The technique is multiply and divide by the conjugate of the denominator. That's every time my example looks like this is going to be my technique. Multiply and divide by conjugate of the denominator. You see here, these two together now, we're going to do the shortcut. What's going to be my new denominator? Do I need to FOIL?
No.
I don't need to FOIL. My new denominator will be what? Square root of 11 square
11
minus 3
9.
square, right? You see that? And my new numerator will be just square root of 11 plus 3. You see, these two right here, this cancel out, I get 11 minus 9, which is 2 over 2, right? Everybody see that? When your denominator looks like this, you multiply and you divide by the conjugate of the denominator. Multiply and divide by the conjugate of the denominator. Okay, so let me give you a couple of examples. Right? Oh. All right. I'll choose these three examples, Okay, since this one is the last one and you haven't done it before, I just do it. So the repertoire to be complete.
Can you scroll down so we can see that bottom one? Or wait, hold on. Yeah.
Like this. Can you see now? All right. I think you have enough time, to think about this. So, can somebody tell me what they did with the first one? Please,
I can.
go ahead, please.
Okay. I did square of 15 plus
Plus,
2 besides, and then I
okay.
did a square of another
Okay, did you do it at the
number.
top also?
Yes. Mhm.
Okay, top and bottom, thank you. And then what is your next step?
And then I do the square of 15
Uh-huh,
and the square of 2 minus
yes,
the square of 2.
thank you. You see, a squared minus b squared. Yep. And this
And then
one
it's
at the top, do you
top.
leave it like that?
No, I put 9 times 15 squared,
Uh-huh,
and then plus 18.
plus 18. You see here, thank you very much. You see here, even if you don't distribute, it's okay. If you distribute, it's okay. If you don't distribute, it's also okay, right? Both ways are okay. So now what is the bottom now? The bottom will be
The
what?
bottom will be 15
Uh-huh,
minus 4.
yep, which is 11. Thank you. And 9 root 15 plus 18. That's a good
I have
answer.
a question.
Yes,
I thought you said when you're multiplying, the numerator had to match the denominator for it to
yes.
cancel out.
The numerator
No,
has
no,
to,
not both the denominators. I'm saying I thought the denominator of the first fraction had to match the numerator in order for it to cancel out.
no, for them to become conjugate, for them to become conjugate, this number right here, we need this number in order to remove the square root from the bottom. But
Oh,
like
wait, never. I'm
when you
confused.
have a fraction, whatever you do at the bottom, you have to do the same at the top, right?
I'm
To
confused.
balance that out.
Got it. Thank
Okay.
you.
Okay, the next one, we have to multiply, divide by what number? Somebody tell me.
Square root of 21 minus square root of 17.
Thank you.
On
And
the
you have
top,
to do it at the top and bottom, right?
right.
So now, what's going to be your new denominator now?
So now it's 4
It's going to be 4. Where's the 4 come from?
from squaring both
Exactly.
square root of 21 and square root of 17. It just makes them the number without the square root sign.
Yep, it's going to be 21 minus 17, which is 4. That's in my new denominator. And the numerator here, we just leave it like that. We even don't need to distribute. We just leave it like that. Okay? If you distribute, it's okay. If you don't distribute, it's also okay. Right? For the last one, okay, the last one is a little bit trickier. But at least we know what you have to multiply by at the beginning, right? You have to multiply by what?
Can I ask a quick question though?
Yeah, go ahead.
So would you not, you shouldn't read, why do I want to reduce the 2 and the 4 in that answer? Oh,
Yeah,
because.
thank you very much. We would reduce the 2 and the 4.
Oh, you do?
It's nicer. It's nicer to simplify it. It's nicer. You see, I even didn't pay mind to it, but it's nicer. Yep, thank you.
Another
That is another extra credit, right?
Well, sometimes I get too far, so I don't know. Then I mess myself up going too far.
Yeah. You see, if you have something to simplify, we don't do it. So it's always nice when you have a fraction that you can simplify to go ahead and simplify it. It's always.
So would that make it a plus? So would that make it plus?
No, it don't make it plus. Just make it negative 1 parentheses square root of 21 minus 17.
Okay.
Yes.
Okay.
The last example, we have to multiply, divide by what? Can somebody tell me?
The square of, I'm at 2 square of 3 plus 4.
Exactly. 2 square of 3 plus 4. This is exactly the conjugate. 2 squares of 3 plus 4. Okay, for this one now, we will distribute the numerator. Okay, for this one now, we're gonna do that. But let's focus first on the denominator. What is gonna be your new denominator?
It's going to be 2. It's like I got a little confused on this one, so I think I did it wrong now that I'm looking at it. But it will be 2 with 3 squared, and you're going to square that.
So here you're gonna square both of them actually. Is 2 squares of 3 all square, right? Minus 4 square.
Yeah.
And if you want to break down now this one square, you have to square both of them. The 2 will be squared and the square of 3 will be squared. It's going to be 2 squared, square of 3 squared. It's going to be 4 times 3, which is 12.
Yes.
Okay, it's going to be 12 minus 16. Now I'm gonna FOIL the numerator. What's that? How much is this?
That is 14 with a square of 3.
Thank you. And what's that?
And that is 28.
And then what that?
And I think I may have done this wrong. It's like I put 2 square of 15.
That is absolutely right. And what's the final answer? I mean the final term.
4 square of 5.
Exactly. So my final answer will be this stuff right here, 14 root of 3 plus 28 plus 2 root of 15 plus 4 root of 5 all over -4, right? You see here also you can simplify by 2, etc., etc. But our goal is just to show you that we have to multiply by the conjugate of the denominator. That is our goal. Multiply and divide by the conjugate of the denominator. Okay? You know, you have some other cases of rationalizing the denominator, but we choose to focus more on the square root, but it could be the cube root also. If I just want to, you know, take a little bit of it, you know, we will not do the cube root, okay? I will not ask you about that on the test. But if it was cube root right now, if this was like, for instance, 1 over cube root of 5, right? You see here, if you want the cube root to go away, how many cube roots you should have? How many?
3.
Is it only 2? For the cube root to cancel out, how many cube roots we have to have?
3.
When you do this, when you do cube root of 5 times cube root of 5, does it make the cube root go away?
Don't you need 3?
We need 3 of them. Exactly, we need 3 of them. If it is cube root, we need 3 cubes, right? We need 3 cube root for the cube root to cancel out, right? You see, that case is a little bit more complicated than the square root. The square root, we just need 2 of them. But the cube root, we need 3 of them, so they become 5, right? You see here, I have 1. How many I am missing?
2 more.
I'm missing 2 more. You see, I have to do that, right? Okay, but we are not doing this case. We are not doing this case. We just, you know, we just do the square root, okay? We just wanted to let you know the technique of rationalizing the denominator if you are squared. On the test, you will see this very small, very simple example, and this one, which is a little bit more elaborated, right? Okay, that's what I see on the test. Okay, do you have any question about that topic? It is a very small topic, right? But, you know, very important in math. You know, like I said, you know, if you keep doing math, you're going to see why. You're going to see the reason why we do that in the first place. If you keep doing math, right? Why we rationalize the denominator, okay? So, and that closes up this section right here. So And then the section 3.6 called a rational exponent, right? What you call a rational exponent. Since we have seen radicals, it allows us to define what is a rational exponent. Look at the exponents that we know so far. We know what is a positive exponent, we know what is a negative exponent, but we don't know what is a rational exponent. For instance, all of us know what is 2 to the 4th power. We all know that it's 2 times 2 times 2 times 2, right? We know what is a positive exponent. All of us know what is a negative exponent. 2 to the negative 3, for instance, is 1 over 2 to the 3rd power, right? We know what is a negative exponent. What we don't know is what is an exponent that is a fraction. We don't know that yet, okay? And that is what you're going to define today. We're going to define what is an exponent that is a fraction, okay? So for instance, we're going to define, for instance, what is 8, okay, to the 2/3 power. You're going to define that, you see? We're going to, right now, we are about to write what is 8 to the 2/3 power. We are about to define what is that exponent, what we have to do to find that number. Okay, that is our new section, 3.6, which is a rational exponent, right? 3.6 is rational exponent. Okay, so we're going to define that. We're going to say a to the m over n power, right? See, a to the m over n power. Actually, this contains two actions, right? The first action is the numerator is a power and the denominator is a radical, right? This is going to be is nth root of a to the m power. Okay? So what you say here is the denominator is a radical and the numerator is a regular power. So, or you can write, you can do the vice versa. You can do nth root of a and then raise it to the m power. Both ways work. You can apply the radical first and then raise it to the power, or you can raise it to the power and then apply the radical next, right? But every time you see a rational exponent, an exponent that is a fraction, has two actions. You're going to raise to a power and you're going to take the radical, right? For instance, we say 16 to the 5/2. Okay? How to calculate 16 to the 5/2 power? How to calculate that? The 16 is a regular power 5. I mean the 5 here. And this is the square root. Okay? You're going to raise to power 5, take the square root, or you're going to take the square root, raise to the power 5. Okay? So if I elect to do this monthly, if I want to do this monthly, what action, if I want to do it monthly without the help of a calculator, what action it takes more sense to do first? We're going to do two actions, right? We're going to raise to power 5, and we're going to take the square root, or vice versa. What action, if I want to do it monthly without the help of a calculator, What action? It just
Do the
makes sense to
square
do
root.
first. Take the
The
square
square
root,
root.
because the square root, what's going to happen? What's going to do to your number? Going to make it smaller, right?
Yes.
If my number is smaller, then I have, can one of you do raise 16 to the 5 power without a calculator?
No.
I was thinking you guys can do it. I cannot do it, right? But I was thinking you can do it. So it's very hard to raise 16 to the 5th power, right? So what you're going to do first is to take the square root of 16, right? So that is easier. If you want to do the mental math, we're going to take the square root to 16, and then we're going to raise it to the 5 power, right? Easier. So how much is square root of 16?
4.
4. And 4 to the 5th power is 64 times 4, which is 320. Okay. But you could do the vice versa, but I guess here the vice versa will be way harder, right? So how are you gonna write 8 to the 2/3 power? What is the radical form of 8 to the 2/3 power? What is the radical form?
It would be 8 cubed.
A cubed or what? The over 3, because it's over 3, it's gonna be what? What radical is gonna be? Cube root, right? You see? You're gonna say the cube root of 8, and then you're gonna raise it to second power. This is cube root of 8 raised to the second power. Everybody sees, how we go from this form to this form. Everybody see that? Everybody see that? This is the numerator is a regular exponent. This is square, right? Is a regular exponent. The denominator is always a radical. Always. The denominator is going to be always a radical, right? This is the index of the radical. If it is 2, it's going to be square root. If it is 3, it's going to be cube root. I'm talking about the denominator. If it is 4, it's going to be fourth root, etc., etc. Right? So now, how much is cube root of 8?
2.
2. It will be 2. This is 2 right here. And 2 squared is what?
4.
4. Okay. So can you try to calculate 64？Go ahead. Try to calculate these two numbers. Okay, so 64 to the 2/3 power. So what do you prefer to do? The cube root first or the square first? What is easiest to do?
I do the cube root.
Cube root first, right? You say it's cube root of 64, and then we're gonna square that, right? How much is cube root of 64?
4,
Is 4. So 4 squared is how much?
16.
16. 35 to the 4th over 5th power. Of course here we're gonna start with the 5th root, right? So 5th root of 32, and then we're gonna raise it to the 4th power, right? How much is 5th root of 32? Is that a known number?
Is it 2?
It is 2, because 2 times 2, 5 times is 52. It's 2 to the 4th power, which is 16. So now, look, because of that, what is going to be then, for instance, what's going to be then a to the 1/2 power? Can you write what is a to the 1/2 power then?
Square root of a to the 1.
Thank you very much. It's square root of a to the 1 power, which is just the square root of a. So basically, another way to write square root is to raise number to the 1/2 power, right? Square root and the 1/2 power is exactly the same, okay? So for instance, when you see 9 to the 1/2 power, you read what? Square root of 9, right? Which is 3, okay? When you see 25 to the 1/2 power, is just square root of 25, which is 5, right? So the 1/2 power is a square root. What is a to the 1/3 power?
A cubed.
A to the, I mean, we say cube root, right? It's cube root of a, okay? You see, all the exponents, 1/2, 1/3, 1/3, 1/4, etc., they are radicals, right? 1/2 is the square root. 1/3 is the cube root. 1/4 is, you know, the 4th root, etc., etc. 1/n, a to the 1/n power is the nth root, right? Let's say my calculator, so can you see my calculator? Yeah, you can see. So let's say my calculator does not allow me to put, you know, 5th root, for instance. My calculator doesn't allow me to put 5th root, okay? You know, I wanna calculate the 5th root of 32. My calculator doesn't allow me to find 5th root. You see, I don't see no 5th root here, right? I don't. So since it's asked me what is the 5th root of 32, you see, it's asked me what is 5th root of 32, and my calculator doesn't allow me to put 5th root, it just only allow me square root or cube root. I remember this, is 32 raised to what power? 1/5, right? 32 raised to 1/5. Now let me try to do it now. Is 32 raised, you see, I put raise here, I put parentheses, 1/5, you see, and it's gonna be 2, you see. That is very, very, you know, very useful if your calculator don't have cube root, if your calculator don't have 4th root or 5th root. That is very useful to know that. Okay.
Can you do that again, please?
I say 32 I say 32, right? Raise is x to the y power right here. Okay. Some people, they have the hat. Some calculators have, you know, some calculators have this. Okay. But mine, it has x to the y power. I put raised to, you see, it generates a hat. And since 1/5 is a whole expression, I put parentheses around that. I put parentheses, I open my parentheses, I put 1/5, I close my parentheses, right? And then I say equal to. See? All right. So that is the rational exponent. So now, does it change? Okay, the exponents are new, but the way we deal with exponents, whether they are rational or not. You see, for instance, we say 5, not 5. We say a to the 1/3 power times a to the 3 power. You see, that right here, every time we multiply exponents, what we do to them? What is the rule?
You add them.
You add them up. The only thing now here, the addition will be a little bit harder, right? You see, everybody will be glad to do. Everybody would be glad to do a to the 4th times a to the 3, right? Everybody will say, oh, this is a to what power?
7.
7, right? And the 7 will come very quickly, right? The only thing here, we do the same rule, but the answer will not come very quickly because we don't like fractions, but it is the same rule. It's 1/3 plus 3, right? Okay, the rule does not change. The fact you have different numbers, different type of numbers does not change the rule. The rule is the rule. You add the exponent. Now, can you tell me when you add 1/3 plus 3, what fraction is that?
3 and 1/3.
That is a mixed number. You see, we don't like mixed numbers as exponents. It's confusing, right? we're gonna write it as a single fraction, right? You see, we write 3/1, right? And then what is the LCD?
3.
The LCD is 3. We multiply by 3. We multiply by 3. It's going to be 1 plus 9/3. It's going to be a to the 10/3, right? What we're going to do next time, we're going to practice this.
Can you say that again?
Yeah, so when you have to do the fraction 1/3 plus 3, we're going to view the 3 as a fraction also. We write 3/1, right?
Mm-hmm.
And we look at the two denominators, we say the LCD, the least common denominator is 3, right?
Oh, right.
And to make the second one become 3, we multiply by 3 here, and we multiply by 3 here, right? So this way, we will be 1/3 plus 9/3. And now we add the numerators, it's going to be 10/3, okay?
Okay.
So the rule will be the same. We're going to practice that next week. The rule will be the same, but what's going to think is harder because we don't like fractions. If somebody does not care about fractions, it is the same thing. If I don't care about fractions, if for me, adding fractions or adding regular numbers is the same for me, then the rules are exactly the same. All right, and we're going to do that next time, okay? So meanwhile, I will go ahead and grade your quiz. So I will put the grade on Brightspace probably in the next couple of days, and yeah, I hope everybody did the quiz normally. All right. Thank you very much, everybody.
Thank you.
Thank you.
Thank you, and you have a nice day.